Etiology of childhood obesity, biological factors. The objective of this class is to understand how genetic, environmental, and microbiological factors influence childhood obesity, highlighting the importance of early prevention and the development of more effective therapies through the study of genetic polymorphisms and the gut microbiota. Obesity has been part of humanity since its beginnings, but not all people exposed to the same conditions develop obesity. This raises the question of what truly determines the propensity for this problem. Various studies, such as those conducted with identical twins separated at birth, have shown that genetics play a key role in obesity. Despite growing up in different environments, these twins have similar weights, suggesting that genetics strongly control body weight regulation. Obesity is a multifactorial disorder. However, advances in the study of genes have revealed important aspects for deeply understanding this problem. Alleles, different versions of a gene that can be found in specific locations on chromosomes, loci, exhibit variations known as polymorphisms that influence traits such as obesity. One common type of genetic variation is the single nucleotide polymorphism, SNP, and some of these polymorphisms have been directly linked to obesity. An example is the FTO gene and its polymorphism Rs9939609, which is associated with a greater tendency to regain weight after losing it. In Latin America, at least 16 loci have been identified as related to childhood obesity, and polymorphisms such as Rs9939609, Rs1421085 and Rs1056513 are common in people with severe obesity. Although the use of specific polymorphism identification is not yet widespread, it is expected that its application will increase over time. Both genetic and cultural variations among different ethnicities are at least necessary, if not fundamental, to understand differences in the prevalence of childhood obesity. Certain genes not only influence weight but also have pleiotropic effects, meaning they can affect various aspects of health. Some obesity-associated genes are activated from birth, partly influenced by the gestational mother's weight. Preventing the pregnant mother from gaining weight beyond what is recognized as appropriate can act as a protector for the newborn even before birth. Science is looking for new alternatives for conditions such as obesity. Research into new genetic, epigenetic, and nutrigenomic techniques is generating advances that any healthcare professional should be aware of. Breaking traditional or minimalist approaches that attribute the problem solely to external circumstances has not nearly resolved the increasing trend of cases, particularly in children. The study of genetics offers opportunities for the development of new, more effective therapies. For example, alterations in the leptin-melanocortin pathway, which regulates energy balance, are common in obese children in developing countries and could provide new insights into treating childhood obesity. Obese parents promote habits that create obesogenic environments for their children, compounded by circadian cycles and genetic factors that tend to have a greater impact on low-income families. It is important to emphasize that obesity has physical, emotional, and social consequences. In addition to genetics, the gut microbiota also plays a crucial role. The microbiota, which includes the microorganisms inhabiting the gut and the set of genes that make up its microbiome, is primarily formed during birth and breastfeeding. Its composition can directly influence metabolism and the risk of developing obesity. In rodent experiments, it has been shown that transplanting the microbiota of an obese mouse into a normal weight one induces an increase in fat accumulation. Damaging the microbiota, depending on the specific microbiome, can cause an energy imbalance that affects glucose receptors, preventing glucose from entering cells. This induces type 2 diabetes in some people. Eubiosis and dysbiosis are terms that describe the balance or imbalance of microorganisms in the body, especially in the gastrointestinal tract. In eubiosis, there is a balance between firmicutes and bacteroidetes, which are the two main groups of microorganisms in the gut microbiota. An imbalance or alteration in the normal composition of the microbiota, dysbiosis, can lead to consequences such as obesity or disorders like irritable bowel syndrome. Eubiosis is crucial for digestive health, the immune system, and general well-being. Xylooligosaccharides are prebiotics that show evidence of improving gut health by promoting the growth of probiotic microorganisms, particularly from the Bifidobacterium and Lactobacillus genera. When consumed between 1 and 4 grams per day, they promote eubiosis. They help by increasing the production of short-chain fatty acids and improving immune function. These compounds are found in common foods such as whole grains, in the husk, vegetables like onions, apples, carrots, and legumes. In conclusion, childhood obesity is a complex phenomenon that cannot be explained solely by the modern environment. Although factors such as diet and lack of exercise play a role, genetics and the microbiota are key determinants. Research in these areas opens the door to more specific and effective treatments that could improve the management of obesity and its consequences, starting from an early stage of life, and even before birth, by controlling factors such as the weight of pregnant mothers.